Okay, let's investigate springs. Let's imagine we have a wall, a spring attached, and we're going to hook up particular mass to the spring. And let's imagine that the surface into which our mass is lying down is frictionless. Let's consider the position where the spring is neither stretched or compressed. I'm going to call this position x naught to refer as my initial position, and this will refer to what I will also call equilibrium. So equilibrium from a spring will refer by convention to the position at which the spring is neither stretched nor compressed. Now let's imagine that now I want to play with it and I want to stretch the bugger to a new position x2, or since I use x naught, let's use x1. So imagine that you're stretching the spring. So I'm going from this position x to this position x1. Therefore I'm displacing my object by delta x, which is in my case x1 minus x naught. Now imagine what's going to happen as you stretch the spring. Obviously, if you let it go, this mass m will try to come back towards equilibrium, and eventually you're going to have an oscillation. So as soon as you release this object, you will see that this object will try to move back to position x naught. So somehow you can guess that there exists a force that will try to move this object back to position x naught. So it will try to bring back the system to equilibrium. And then if you ever play with springs, you will notice that if you stretch the spring just a little bit, so that delta x is a low number, versus if you stretch it to a large amount, it's going to be much harder to hold it if you stretch by a big amount. So you kind of feel, if you play with a spring, that the force somehow depends on how much you stretch it. The more you stretch a spring, the harder it's going to be to hold it in position. Therefore, you can imply that the force that will try to bring it back to equilibrium will be larger, and the lower or the smaller the delta x, the smaller the distance between equilibrium and new position, the smaller the force. So from experiment, we kind of guess, and we already know, that the force somehow is proportional to the displacement. The more you stretch the spring, the stronger the force will be that you will feel, and the force that you will need to apply to maintain it at equilibrium. The lower this displacement, the lower the force. So there is a direct relationship between the two. So indeed, this must look like a line equation. So F must be somehow proportional to delta x, such that we have a line equation. What we have to figure out is what is proportionality constant. In this particular case, we will call it K. So this is how the force due to a spring, which I will write Fs, is usually defined. It's directly proportional to how much you stretch it, and it will be multiplied by a particular number, which we will use K to represent, and K will be defined as what is known as the spring constant, which is just a number that will represent how stiff the spring is. So the harder it is to stretch a spring, the higher K will be. The easier it is to stretch a spring, the lower this number will be. So this number is directly from experiment, and they represent the stiffness of the spring. So a spring that you will find in a toy box for kids will most likely have a very low K. While if you pick up a spring from your car, the suspension spring, those guys, good luck if you want to stretch them. Much higher K number. So the K can go all the way up to 1,000, 10,000, or as low as 1, 2, 3. So usually in the experiment for this class, you will be dealing with spring constant of 1, 2, 3, 4, up to 10. Now, what is the units of that little constant? Well, let's do a little unit analysis. Fs, this is a force, therefore the units must be Newton. Then we have the units for our k, which we don't know, and this must be multiplied by delta x, which is a distance, because it's a displacement. So the units must be meter. Therefore, the units of my little k must be Newton per meter. That is, if we plug back this in here, Newton per meter, this cancel, and Newton is equal to Newton, so that will work. So the units for k is usually given as Newton per meter. Now remember that you can re-express Newton as kilogram meter per second squared. If you do this, you will divide this by meter again. Therefore, meter cancels out. So you might find these units. So the units for k is either Newton per meter, or you might say it as kilogram per second squared. Those two units are equivalent. Okay, now sometimes you will find this version of the spring force. Sometimes you will see a little negative sign. What does that mean? What it means is that it wants to reflect the fact that this is a restoring force. Example, your system is at equilibrium, now you're going to stretch it. Your displacement is from here to here, that's your dx. But the force that you will feel as you have displaced that object, which will tend to restore the object back to equilibrium, is obviously in this direction. Therefore, since the vector f is opposite to the direction of delta x, there must be a negative sign. So this negative sign that you will see in some version of the spring force is only here to remind you that f is always in the opposite direction as delta x. That is, if you're stretching the spring, f, therefore in this case towards the right, f must be towards the left. Similarly, instead of stretching, you're going to compress the spring. Now your delta x is from here to here, and the force that you will feel will tend to go in the opposite direction, again in order to bring back the system to its equilibrium position. So in all cases, whether you stretch or you compress, the force is always going to be opposite to the displacement delta x, which is the reason why we have a negative sign. Now in general, and for calculation, especially as you use the force due to the spring into your sum of the forces equal to ma, I would strongly suggest not to use the negative sign, which means you can stick with this in scalar notation. That's perfectly fine. This assumes, of course, that you start from equilibrium. If you start from any other point, this must be x final minus x initial, which was our delta x. But I would strongly suggest that you leave it as a positive value. Whenever you're going to be doing a particular analysis and you check the direction of your force with respect to your coordinate system, then you will put the negative sign if appropriate. Okay, let's graph this. We know that this is the magnitude version of our frictional force. This, hopefully to you, but at least to me, looks like a nice line equation. So instead of putting x versus y, I'm going to plot fs versus x, or delta x. And I know that if I plug this versus this, I'm going to get a straight line whose one of the points is at the origin, so that line must be going through the origin, and the slope will be representing my k value. So if I have a low k value, I have a low slope. If I have a higher k value, a higher slope. Even higher k, bigger slope. So this would be, say, k is equal to 10, k is equal to 5, k is equal to 0.5. So we see clearly that if you apply a particular force, let's say 1 Newton, to a spring of a K constant of 10, you will displace it by, say, this amount, 0.1 meter. If you apply the same force to another spring whose spring constant is less, therefore it's easier to stretch it, because K, remember, represent the stiffness, then you expect the delta X to be bigger. Sure enough, it's going to be bigger. And if you pick now another spring whose spring constant is even less, very small value K, therefore you expect that this K is very easy to stretch and compress. If you apply that same force, obviously the delta X will be even bigger, let's say 1.2. So you can graph F versus dx and you will have a nice representation of the spring behavior, because you know that the slope will be exactly correlated and equal to the spring constant. Now, of course, if you're dealing with this functional form, then you will have the exact same graph, except everything will be negative due to this. No worries, the slope will still give you, the magnitude of the slope will still give you K. So in this case, you have, let's say the slope is -2, then you know that this -2 refers to the whole thing, therefore K is equal to 2. So remember, K is always positive. This negative sign comes from this one, which also comes from the negative slope. So slopes are in springs are nice and easy. Let's look at an example. Let's say you have a spring. This is my equilibrium position. I'm going to stretch it to this new position. So I'm going to set my x0 to be equal to 0. That's where I will define my coordinate system y and x. So I chose to set up my center of my coordinate system at equilibrium so that I can use directly kx instead of x minus x0, since x0 is equal to 0. I'm going to move this object to position x1, say 2 meters. Let's do a free body diagram on this object. Well, obviously we have the weight, we have the normal force, and we have this force due to the spring acting on our object. So the force due to the spring acting on our object is this one, which must be going back to equilibrium position, therefore towards the left. So if you want to write sum of the forces is equal to ma in the x direction, based on my current system, F is going towards the left, therefore minus kx must be equal to ma. If I know the displacement x or delta x, and let's say k is 10, then I have minus 10 times 2 is equal to m, let's say 1 kilogram, times a. Therefore, a is equal to minus 20 meters per second. The minus sign tells me that it's going in the opposite direction as the one that I decided to be positive. So you can now treat this force as any other force, such as normal force, weight, spring, friction. The only advantage of this is you know its magnitude, it's kx, and you will usually know its direction, because the problem will always tell you in this particular position where your system is, your spring is being stretched by, say, 0.5 centimeters, or is being compressed by 0.2 centimeters. If the spring is being compressed, then you know that the force is going away from the spring. If you're being told that the spring is being stretched, then you know the force is going back to the unstretched position. So depending on what the problem tells you, you usually will know the direction of the force, because you know that the direction of the force is always towards the equilibrium position of the spring. And you will also always know its magnitude, just kx. Now watch out, when we write kx, we always implies that we start from the origin. If you start from an already compressed position, such that if this is your equilibrium position x0, and your system start already at x1, and then is being moved to x2, then obviously this force, the force needed to go from here to here is going to be k delta x, which is kx2 minus x1. So remember, we use just kx if we position our current system initial at the initial position. Otherwise, you have to keep the general functional form. And again, remember that if you want to use the negative sign, it's usually only here to remind you that the force is restoring force, which means the force will tend to bring back the system at equilibrium. We call it a stable equilibrium. In nature, most of our system have stable equilibriums, but many have unstable. So a stable equilibrium would be like this, unstable would be like this. If you move the system away from equilibrium, such as a spring, you stretch it, it will tend to come back before you oscillate. They will always try to come back to equilibrium. Versus other system where the equilibrium is here, if you move it away from equilibrium, it will go away even further. It will not go back to equilibrium. So the spring would be this case of what we call a stable equilibrium.